That's so weird. I don't know why it does that. Anyway, so AP Classroom is alive and well. It's back up and running. So if you were a person that was not able to access the original assignment on AP Classroom, or if you were a person that just didn't do the first assignment for whatever reason on AP Classroom, it's reopened. Okay, so please, sometime in the near future, jump back on AP Classroom and do it, and then we'll use it moving forward. Again, the reason why I want to use AP Classroom is because it is authentic, real AP questions, right? Eventually, later in the year, once we get closer and closer to that test, there's no better way of studying for the AP test than looking at authentic questions. So my goal here is with that AP Classroom is to kind of just slowly but surely roll them out to you guys all year long. All right. Homework topic 3 is due by Friday at midnight. So you got all week to work on homework topic 3. I'm hoping that stays true. We've got some stuff to cover this week. I'm not fully convinced we're going to get through everything I want to get through this week with how big topic 7 is. Topic 7 is a pretty large topic, so it's going to take us a couple days. But anyway, that's kind of all I have. Please type here in the chat. If you're reading these first 2 questions, try them. Think about them, okay? Please read through the first 2 questions that I have. If you want to write them somewhere else on your sheet, awesome. If you just kind of want to go through them in your head, that's fine too. But let's start with that. I'll give you a minute or so. If you haven't thought about them, please think about these 2 questions, and then I'll jump back in and we'll get started for the day. All right, so for this first question, welcome back, Amy, by the way. It's good to see you, made it back. Anyway, so for this first question, okay, I'm asking you, how can you determine the order of the orbitals within an atom? So I've given you two ways of doing this, right? The first way is using the periodic table. If you look at the periodic table and treat every little element box as an electron, and if you realize that we have these different blocks of the periodic table, the S block, P block, D block, F block, you can kind of just count up the electrons and start a new orbital whenever you hit the next block, so to speak, all right? That was one way we had gone through that. The other way, and I'll draw it again, is this little kind of picture, or this from memory. If you're able to draw this picture, you can get the order every single time absolutely correct. All right, so here it goes. All the s orbitals, all the p orbitals. Oops, I don't know what I'm doing here. Hold on. The d orbitals and the f orbitals. Okay, if you can draw this from memory, you then draw these diagonal arrows to get the correct order. Okay, 1s, 2s, 2p, 3s, 3p, 4s, 3d, 4p, 5s, 4d, 5p, 6s, so on and so forth. Okay, I can tell you that there are kids and there are students all over the country on their AP chemistry test. One of the first things they write down on the very first page is this, so that they don't have to think about it. They memorize this little setup, they memorize how to draw this, and then essentially you're good to go on the order of the orbitals. All right. So I said this last week like 4 times. I'll say it again. It doesn't matter which method you use. If you are comfortable looking at the periodic table and deriving the order by kind of just going along each little box, counting up the electrons, awesome, it works. If you're comfortable kind of memorizing this, or if you're in the process of practicing maybe memorizing this, this gives you the order too. Whichever of those is perfectly fine. But somehow, some way, you've got to be able to get the correct order of the orbitals. Was that a here chat or was that an actual question chat? Come on, chat. Do something. These Chromebooks are just awful. I sincerely hope you maybe have a different device at home, because these Chromebooks are just miserable sometimes. Yeah, it's not even loading. All right, forget it. If that was an actual question, I apologize. I'll try to take a peek at the chat in just a little bit. I'm hoping it was just a here. But anyway, so the second part here is write out the electron configuration for tellurium. That's element number 52. When you write out the electron configuration, this is where this order comes into play, right? We want to get the order of this correct. All right, so we start with 1s. I have 1s, 2 electrons, 2s, 2 electrons, 2p, 6 electrons, 3s, 2 electrons, 3p, 6 electrons, 4s, 2, 3d, 10, 4p, 6, 5s, 2, 4d, 10, and unfortunately I got to wrap all the way around here. I'm just going to go way back over here. And last but not least, 5p. And how many we got in the 5p orbital? 4. And that is the electron configuration for tellurium. Again, the order of those orbitals, you can figure out by either looking at the periodic table, or you can figure out by doing the arrows up above. So if you trace those arrows from tail to head, you'll get the correct order. All right. Of course, we can abbreviate this. We don't have to have this long, miserable electron configuration. We could go back to the previous noble gas, which in this instance is krypton, element 36. And I could start from that point on. Okay. So this is perfectly fine. It just takes a long time. I could have also written it out as krypton, and then 5s2, 4d10, 4p4, or 5p4, I'm sorry. Okay, like that. So I hope that makes sense. And again, the way you get these wrong, right? How can you get these things wrong? You can have the wrong order. That'll screw it up really quick. Or you can get the wrong electrons, okay? So every s orbital comes in sets of 1, so it can hold 2 electrons. Every set of p orbitals comes in 3 orbitals. It's a set of 3, so they can hold 6. The d orbitals come in sets of 5, so they can hold 10, all right? And then we just got to make sure that all of our little exponents here add up to the correct total number of electrons that we need. So we have 2, 4, 10, 12, 18, 20, 36, 30, 38, 48, and 52. So we're perfect. Okay. All right. So let me jump back into where we were yesterday. As a part of yesterday's video, we started topic 1.6. So if you have the 1.6 sheet, please grab that out. We're going to try to finish that today. It's a little dense. Some of these questions are a little tough today, but I'm going to try my best to slowly but surely give an accurate explanation behind why the right answer is the right answer, and so on and so forth. But until we get to those questions, let me just kind of recap and start fresh with this topic for you guys, and just give you a quick 5-minute kind of restart. So photoelectron spectroscopy, which is 2 massive giant words which look kind of scary. It's an instrument, okay? It's a big giant instrument, as you can see in this picture, of it's an instrument used in chemistry to analyze chemical samples. So what this instrument does is, if you put a sample of a pure atom in there, a pure element in there, okay, this instrument will bombard that sample with extremely high energy electromagnetic radiation. Okay, now high energy electromagnetic radiation is either X-rays or gamma rays. Okay, nasty stuff. If your body is exposed to X-rays and gamma rays, it can cause cancer. All right. So again, when you take an X-ray at the doctor, they put that big giant lead shield over whatever they don't want an X-ray of, and in theory, to protect you, right? And sorry, I don't mean to say in theory. It does protect you. That sounds awful. No, it does protect you. Okay, but too many x-rays, right? Or if you're getting hit with x-rays on a consistent basis, they absolutely do cause cancer. All right. So side note, nasty stuff. All right. These instruments are extremely expensive things. I haven't priced one out ever, but I'm pretty confident that they're over $1 million a piece. When I was at UWSP, we didn't have one at the university in Stevens Point. They might have one now. I'm not quite sure if they do or not. I'm sure Madison obviously has one. They might even have two. But these are very, very expensive instruments, but they do really powerful things too, okay? So when these atoms get hit with this high energy electromagnetic radiation, it essentially strips all of the electrons from that sample. And that's useful because with that information, we can determine which orbitals or where the electrons were in that atom, okay? So what happens is you get readouts like this. This is a generic PES, which stands for photoelectron spectroscopy. This is a generic PES spectrum, all right? Let me give you the rundown of how to read this thing. Your y-axis over here, all right? Think of this as your nucleus. Okay, that is your nucleus of your atom. As you read left to right, or as you go left to right across the x-axis, each peak you hit is the next orbital in sequence. So we know the order of the orbitals, or I should say, we're learning the order of the orbitals. We're hopefully getting a little better at that. But this is my nucleus. The first orbital that I hit is going to be 1s. The next orbital that I hit is 2s. And then 2p, so on and so forth, if I were to have more of those, right? So think of this y-axis as your nucleus. And as we read left to right, the orbitals or the peaks represent those orbitals in the order that they're supposed to occur, okay? The height or the intensity of those peaks, this is related to the number of electrons. This height, because it's an s orbital and the s orbital is full, this height must equal 2 electrons. We know that an s orbital is a set of 1, and each one can hold 2 electrons. This must represent 2. This is the same height. It must also have 2 electrons. This one's a smidge taller. It's got like 50% more, right? So this must represent 3. So in total, in this atom, we have 2 electrons, 4 electrons, and then 7 electrons. And this is nitrogen, okay? I went through that in yesterday's video. I know I did, but I'm hopeful that if by kind of sleeping on it for a night and coming back to it, I hope that makes sense. The other thing that I pointed out yesterday and that you'll notice today as well, the x-axis, numerically speaking, is completely backwards, right? 0 rather, right? If we kept going further off to the right, you would hit 0. And near the origin, or way on the left, we have bigger numbers. On this graph, our origin is near 100, okay? It's backwards. It's weird, it's funky, but the reason why they set it up that way is so that you can read it just like I've read it right now. If you make your y-axis your nucleus and you read left to right, the orbitals or those peaks represent those orbitals in the order that they occur. So I hope that kind of makes sense. And by the way, please unmute and you know, pop a question. If you have a question, that would be great. I would love to explain things a little further or slow down if need be, whatever the case may be. But please feel free to unmute and ask something if you need to. All right, number 2. On the photoelectron spectrum of magnesium, draw the spectrum of aluminum. Okay, let's get the lay of the land first. Let's try to figure out what we know and where we're going here a little bit. So we know magnesium is element number 12, and it has 12 electrons. Okay, aluminum is element 13, and it has 13 electrons. Okay, so this right now represents magnesium. This is my nucleus on this graph. And as I go left to right, I'm going to go in order. 1s, 2s, 2p, 3s. The height of these peaks represent the electrons. So 2, 4, let's see, That must be 6, right? Because it's a p orbital and they can hold 6. So 2, 4, 6 more is 10, plus 2 is 12. Excellent, it matches, that makes sense. This is magnesium, we're thinking about it correctly. We're asked to draw aluminum. Now, there's gonna be a couple differences with the aluminum spectrum, okay, of a PES, or what we're gonna draw for aluminum. The difference is gonna be, we have one extra electron. We'll deal with that in just a little bit. But there's another difference. The other difference is where these peaks are is going to be slightly different, okay? This x-axis, which is usually called binding energy, what this is trying to get at or say is it's the energy that's required to get rid of an electron. All right, how much energy do I need to put in to remove electrons from that orbital? So you'll notice the 3s, which is like less than 1, and when I say less than 1, the unit on that is megajoules per mole. Please don't worry about the units. We will never, ever actually do math with those units. We will never ask what those units are. Think of it more as like just a comparative model for right now, okay? But to remove these 3s electrons isn't too bad. It's less than 1 megajoule per mole. To remove the 1s electrons requires over 100 megajoules per mole. So long story short, it's much harder to remove the 1s orbital electrons than it is to remove the 3s orbital electrons. Okay, so what does this have to do with aluminum? Well, aluminum has one more proton than magnesium. Okay, that extra proton is going to hold or attract those outer electrons a little bit stronger. So as a result, we should expect to see that all of aluminum's orbitals require a little bit more energy to remove its electrons than magnesium. This is Coulomb's law from yesterday's class, okay? Coulomb's law is that weird equation I showed you in yesterday's video. It's related to attractive or repulsive force between charged particles. So the greater the charge, meaning more positive or more negative, right? The stronger the attraction between those two things that you're comparing. So in this instance, we're looking at the nucleus of magnesium with 12 protons and the nucleus of aluminum with 13 protons. That extra proton in aluminum makes the attractive force felt by the electrons a bit stronger. So we get peaks that are left of the magnesium peaks. Each one of these orbitals in aluminum is gonna require just a little bit more energy to get rid of them because of that extra proton in aluminum's nucleus. And if you're wondering, yes, I am just as bad of a drawer as I am a writer. I mean, that's probably not surprising, but you know. Anyway, so the peaks would be left of the magnesium peaks, but we have one other thing we got to account for. We still have that extra electron. That extra electron in aluminum is in the 3p orbital. So we need a whole extra peak in general for aluminum. I don't know where it would be, okay, somewhere out here. But what's important is I would only make it one high. I would only have the intensity of that peak be up to that first little line. And the reason is there's only one electron in the 3p orbital. Okay? I hope that makes sense. Again, the big takeaways are the reason why aluminum's peaks are left or higher numbers than magnesium is that extra proton. That means that the electrons are held more strongly by the nucleus. And again, that extra proton makes it the attractive force stronger. And then the other thing that was different is we added an extra peak for 3p because there's an extra electron as a part of aluminum. Okay? Let's go to number 3. All right, in number 3, which of the following best explains the relative positioning, meaning like, left and right on this graph, and the intensity, which is implying the height, right? The intensity is talking about how tall those little peaks are, of the two S peaks in the following spectra. Spectra is the plural of spectrum, by the way, just to let you know. So we have more than one. They're called spectra. All right. So we have lithium in the top graph. We have beryllium in the bottom graph. And we notice that beryllium's peak, and again, these are both 2s because they told us they were the 2s peak. Okay. Beryllium's peak is way left of lithium's peak. Okay, well, from the last problem, we kind of learned about that a little bit, right? We know that that extra proton in beryllium's nucleus must mean that it's harder or it takes more energy to remove beryllium's electrons. And we see that, right? It's a bigger number. It's shifted left. The other thing we have going on here is the height. The height of beryllium's 2s orbital is twice as high as lithium's 2s orbital. And that also should kind of hopefully make sense. The height of the peak is related to electrons, right? So beryllium has 4 electrons total. The the electron configuration would be 1s2, 2s2. The electron configuration for lithium is 1s2, 2s1. Lithium has 1 electron in the 2s. Beryllium has 2 electrons in the 2s. It makes sense that this peak down here is twice as tall as this peak up here. So let's look at our options. I suppose we could answer the question or look at what we have for options before I go off on my tangent, but too late now. A, beryllium has a greater nuclear charge than lithium. Yeah, that sounds good so far. That's absolutely true. 1 extra proton means greater nuclear charge and more electrons in the 2s orbital. Yeah, that's also true. I think that explains everything perfectly. Okay, A is the correct answer here. Now, I could go through the other ones, okay, but I promise you that we'll get some tricky explanations, especially the next one. Number 4 and number 7 are a little hairy, so we're going to keep going, all right? If you are sort of kind of getting what I'm talking about, please feel free to read them and give it a shot on your own. 5 and 6, I think, are doable, potentially right now with what you know. But let me walk through 4. And again, if you're a little bit ahead of me or if you want to kind of take a peek ahead of me and try these other ones, go for it. That's perfectly fine. I'll just kind of, slowly but surely plod through them. Okay. Number 4, given the photoelectron spectra of phosphorus and sulfur, which of the following best explains why the 2p peak of sulfur is further to the left than the 2p peak of phosphorus, but the 3p peak of sulfur is further to the right than the 3p peak for phosphorus? Okay, first things first. That's a very long question, right? Let's make sure we identify what they're talking about first, all right? They're asking about the 2p and the 3p orbital peaks of these two graphs. So let's identify those first, all right? Again, this is my nucleus, right? And as I go left to right, I identify the orbitals in order. This is 1s, 2s, 2p, 3s, 3p. And same thing down here. That's my nucleus. This is 1s, 2s, 2p, 3s, 3p. So the peaks that the question is asking about are the tall ones, right? We have the 2p peak right in the middle, and we have the 3p peak the furthest right on both of these graphs. Those are the ones that they're comparing in this question. So they're saying, okay, why is sulfur's 2p peak further left? And you can see the value is 16.5. The phosphorus value is 13.5. So this one's further left. But the 3p peak is actually further right. This is 1.00. That's 1.06. Okay. This is counterintuitive. This is opposite of literally what I just told you on the magnesium and aluminum question. So we need to think a little more. Now, here's the good news. Anytime data that AP gives you doesn't match what I've taught you, they don't expect you to arrive at that data. What I mean by that is they wouldn't expect you to know or to guess that this is the way it would be because it's counterintuitive. Having said that, they very well can give you counterintuitive data and then ask for maybe hopefully a legitimate explanation as to maybe why that happened, okay, using your chem knowledge in other places, right? So this makes sense. And the reason why the 2p orbitals make sense is because sulfur has more protons, right? Going to the same explanation we used earlier. Sulfur's got more protons in its nucleus than phosphorus. We would totally expect that its electrons should be held more tightly, or in other words, should require more energy to remove them. But we notice the 3p orbital is the opposite, okay? So let's look at our options down below. Sulfur has a greater effective nuclear charge than phosphorus. Yeah, that's true. That means more protons. There are more protons in sulfur than phosphorus. And the 3p sublevel in sulfur has greater electron repulsions than in phosphorus. Okay, let's look at that for just a second. Electron repulsion. This happens when you have electrons in the same orbital. All right, two electrons can exist in the same orbital. That's perfectly allowed as long as they're spinning in opposite directions. Okay, but that doesn't mean that there isn't repulsion. There absolutely is repulsion. We're still talking about a negative particle and a negative particle in the same area, right? They still will have repulsion between them. So let's just verify this. Is there more electron repulsion in the sulfur 3p orbital than there is in the phosphorus 3p orbital? Well, in phosphorus, up here, we have 3 electrons in the p orbital, and in sulfur we have 4 electrons in the p orbital. Would 4 electrons have more repulsion than 3 electrons? Yeah, I think they would. I think this is the correct answer. A is actually pretty darn good, okay? The first part is true. There's more protons in sulfur's nucleus, and the second part is true. There is more repulsion in sulfur's 3p orbital. Now, does that repulsion make it easier to remove sulfur's electrons? Okay, that's probably like the crux of the explanation here. And that's a tough thing to explain and a tough thing to kind of wrap your head around. So that extra repulsion kind of pushes those electrons further out, okay? It forces them to be just a little bit further away from the nucleus. And as a result, it would make it easier to remove sulfur's 3p electrons, okay? A is the correct answer. I'll talk a little bit about B through D in a second, but, and by the way, like I said before we started this one's nasty. This is a nasty, nasty question. It's very complex and involves some concepts that we just haven't quite dug into yet. So if you're completely lost and you know, not quite sure what the heck I'm talking about, again, these are some topics that are going to come back around in the near future. So hang with me and try to catch what you can, and we'll visit these again later. Okay, so B, sulfur has greater effective nuclear charge than phosphorus. Yep, that's true. That was the first part of the first one as well, so that's still true. The 3p sublevel is more heavily shielded. Okay, shielding is related to the number of core electrons. All right, we are going to talk about that tomorrow in topic 1.7. Okay, shielding is related to core electrons. Sulfur and phosphorus have the exact same core electrons. Again, tomorrow, topic for a different day. Sulfur has a greater number of electrons than phosphorus. Yep, that's true. So the third energy level is further from the nucleus than in sulfur than in phosphorus. Man, that sounds like it wants to be right. It's not quite correct. It's related to radius of atoms. We will talk about that tomorrow as well. Last but not least, sulfur has a greater number of electrons than phosphorus. Yep, so far so good, that's true. So the Coulombic attraction between the electron cloud and the nucleus is greater in sulfur than in phosphorus. All right, so this one is kind of a mess. And it's talking about how more electrons equals greater attraction. It's not perfect. Really, it's the number of protons in this instance that are going to really dictate that. Again, we'll come back to these sort of topics in the next couple of days. This question maybe would have been better to ask you guys probably on Friday than it was today. So I apologize for that, but too late now. Okay. All right. Number 5. This one I think is much more manageable. So let's look at this one. We have a spectra for sodium and potassium on the exact same graph. So we have two peaks of different elements on the same graph. Which of the following would best explain the difference in binding energy for the 3s electrons? And again, binding energy, all that's trying to describe is how tightly or how strongly the electrons are attracted to the nucleus, okay? So why is the 3s peak of potassium way left and requires more energy to get rid of them compared to the sodium peak of 3s, which is way to the right, okay? And the answer is potassium, which is element 19, versus sodium, which is element 11, potassium has way more protons, okay? Those extra protons make it more difficult to remove the electrons. The extra protons have a stronger attractive force to the electrons around the outside. So A is our guy. It's A. It's got to be because there's more protons, which makes these more strongly attracted to the nucleus and much more difficult to get rid of. Part 6. It's a continuation, same exact graph, but a different question. Which of the following would best explain the difference in signal intensity? And again, when I say intensity, I mean the height of the peak, okay? Why is there a taller peak for potassium's 3s compared to sodium 3s? Our options aren't great, so I'm going to kind of explain by writing off to the side here, okay? So potassium, okay? The electron configuration for potassium looks like this. The electron configuration for sodium looks like this. Okay. The peaks represented on this graph are for the 3s orbital. So we're looking at that guy and that guy. Why is the peak of potassium twice as high as the peak of sodium? Well, potassium has 2 electrons in 3s and sodium has 1. That's the correct answer. Now, none of these options are really that great. You'll notice the first one is talking about nuclear charge. That's protons, so that one can't be right. It's got to be out. B is saying that there's more electron repulsion. I mean, that's true, but it has absolutely nothing to do with the height of the peak, so that's irrelevant. C says that sodium only has 1 valence electron. Also true, and I mean, it's kind of related to the number of electrons in the orbital. So we'll leave it for now. Sodium has less electron shielding than potassium. It's true, but again, it has nothing to do with the height of the peak, right? So the correct answer here is C, but I think that's just a terrible answer. Like it's right, but it's just not a great explanation, if that makes sense. This question, I don't know where AP got this question, but it's not the best. But anyway, this is what matters, right? The height of the peak is always the total number of electrons. 3s for potassium is that high because it has 2. 3s for sodium is that high because it has 1. It's half the height of the potassium one. Okay, I hope that makes sense. Again, the correct answer isn't the best explanation that can be given, but I hope my explanation sort of makes sense. All right, last but not least, I'll try to plow through this to get you guys out of here because I have a hunch I'm boring you to death. All right, so this one is complicated as well. Hang with me. I'll try to get through as quick as I can. We have a photoelectron spectrum of scandium, label the peaks with the orbital they represent. So we can do that. I think we feel pretty confident, hopefully, on the order now. Again, nucleus is right here. That's a horrible line, but you get the idea. I'm going to claim the smartboard's not calibrated, but that's probably a lie. That's 1s, 2s, 2p, 3s, 3p, and now 4s, 3d. That's the order. However, we should have 2 electrons in 4s and 1 electron in 3d. So the order has actually flipped. Okay, that's annoying, and it happens, and it's nothing that you would be responsible for understanding when it happens. Okay, so don't just hang with me. This taller peak is 4s, this shorter peak is 3d, even though the order should be opposite. Okay, This happens sometimes with those transition metals. Scandium is a transition metal. It's the very first transition metal on the periodic table. These do weird things, and part of the weird things that they do is sometimes their orbitals get in different orders, okay? There's a reason why, it's just not a part of our class. All right, so here's the question. Which of the following best explains why scandium commonly makes a 3+ ion as opposed to a 2+ ion? In other words, scandium prefers or likes to lose 3 electrons as opposed to just losing 2. Why would that maybe be the case? A, removing 3 electrons releases more energy than removing 2. Okay, to get rid of electrons requires energy. When electrons get removed, it doesn't release energy, it requires energy. So this is actually the opposite of what's truly happening. So A can't be correct. Option B, scandium is in group 3. Okay, so far so good. Group means like column, okay? Group or family is implying a column. So yes, it's in column 3. And the atoms only lose the number of electrons that will result in a noble gas electron configuration. Oh, that feels like it wants to be right, but it's not, okay? Now, I can explain why it's not by using your last year's periodic table. In last year's periodic table, when you looked at some of those transition metals, they had lots of options for charges, right? There was like +2, +3, +4, plus whatever. And some of those elements had 2 or 3 or 4 options of what ions they could form, okay? For example, I could talk about iron 2+. Iron is element 26, and if it loses 2 electrons, it turns into iron 2+. But it doesn't turn into a noble gas with that number of electrons. What I mean is the noble gases have 10, 18, and 36 electrons, okay? And we know for a fact that iron, as an example, can exist with a 2+ charge having 24 electrons. That is not a noble gas electron configuration. So the first part is true. It is in group 3. And the second part feels like it wants to be true because a lot of ions do have a noble gas electron configuration, but it doesn't have to be that way, all right? And the word only is the reason why this doesn't work, okay? Because it's not the only option. There are other options to make stable ions than making it noble gas configuration. All right, part C, the amount of energy required to remove an electron from the 3D sublevel is so close to that of 4s, but significantly more energy is needed to remove the electrons from the 3p sublevel. So let's kind of look at our graph of what they're talking about there. The 3D and the 4s peaks over here are almost directly on top of each other, okay? The difference between one to the other is 0.14 megajoules per mole. I mean, they are very, very close. So the first part of this is absolutely true. The second part saying we need way more energy to get rid of 3p electrons. And that's kind of true too, right? If these are both less than 1, in order to get rid of any of the electrons from this orbital, we'd have to add 5 times the energy, okay? In terms of like a multiplication sign, right? We'd have to add 5 times the energy to get rid of the 3p electrons. C is the correct answer. All right. And again, it's a little funky. These aren't, 4 and 7 especially were nasty questions. Let me just talk about D really quickly. Removing 2 electrons alleviates the spin pairing repulsion in the 4s sublevel. So this is talking about, again, you have 2 electrons in the same orbital, they repel. If you get rid of some electrons, it alleviates that repulsion. Yeah, that sounds pretty good. So it is not as energetically favorable as emptying the 4s sublevel completely. All right, so here's my issue with option D. If we take 2 electrons away from this atom, those 2 electrons are going to get taken from the valence orbitals. The valence orbital in this atom is 4s. It's the highest energy level s orbital. So if I were to remove 2 electrons from 4s, if I was to remove 2 electrons from this atom, I'm taking both of them from 4s. And the second part is like contradicting or trying to say the exact same thing, okay? If you remove 2 electrons, it alleviates the repulsion. Okay, sounds pretty good. But it's not as favorable as emptying the 4s sublevel. Well, if I took 2 electrons, I did empty the 4s sublevel because that's where the first 2 electrons would get taken from. So it's kind of like contradicting itself right in the middle of the sentence. But Anyway, so it's not D either. It is absolutely C. All right, that was very dense. I'll kind of stop here. Again, let me recap really quickly. PES, or photoelectron spectroscopy, what you are responsible for more often than not is to understand how to identify which peak equals which orbital. Okay, so knowing 1s, 2s, 2p, 3s, 3p, so on and so forth, you're responsible for that. The way you can do that is by identifying the y-axis as the nucleus and then go left to right across the graph to get the correct order. The other thing you're responsible for is understanding that the height of these little peaks represents the total number of electrons in that sub-level of orbitals. This is 2 electrons, 2 electrons, 6 electrons. The reason why this can hold 6 and this can hold 2 is because s orbitals come in sets of 1, p orbitals come in sets of 3, okay? The other thing, the very last thing that you're responsible for with PES is the further left a peak is, the harder it is to remove those electrons from that atom. And atoms that have more protons hold their electrons more strongly, okay? So that was like the comparison we made with right here, magnesium and aluminum, right? Aluminum has an extra proton. Its peak should be further left because that extra proton has a stronger attractive force to its electrons, okay? That was very dense. I'll shut up. Please have a lovely day. I hope I didn't ruin your afternoon. We'll catch you guys tomorrow. Please hang around if you have a question. Other than that, we'll see you guys later. Thank you.